Hi folks, Chris McClure here. We're going to continue talking about solving quadratic equations, but this time we're going to look at the possibility of having to expand our system of numbers into the complex number system. So that's what we will talk about today, so that every quadratic equation now can be solved. Now, first, let's talk about what an imaginary number is. We have the letter I, which is really a number. I know, it's the same old situation where we have letters representing numbers, but I is going to be that number that is the positive square root of -1. Okay, in other words, I squared is equal to -1. When we talk about a complex number, that's going to be where we have some real number like a plus some other real number b times I. So for example, 2 plus 3i. Any number that you could write in the form of a plus bi, where a and b are real numbers, then that's a complex number. And in fact, any real number, like for example 4, could be written as a complex number, because you could write it like this: 4 plus 0i. Now, when you are looking at a complex number, a plus bi, the real number by itself is called the real part. And the other real number that multiplies I is called the imaginary part. So if you have a plus bi, a is the real part, b is the imaginary part. Now we're going to talk about combining real numbers by adding, subtracting, multiplying, and dividing. Okay, now to start off with, let's talk about equality, as in two numbers are equal only if and only if the real parts are together or equal to each other and the imaginary parts are equal to each other. Okay, that should make sense. If you have 2 plus 3i, well, the only number that's going to be equal to it is a number where the real part has going to have some numbers that add up to 2, plus an imaginary part where the numbers add up to 3 as well. Now, when we talk about adding two numbers, well, all we need to do is add the real parts together to get the real part of the sum, and when we add up the imaginary part together to get the imaginary part of the sum. So, as we shall say, if you have this example, 2 plus 3i plus, say, 5 plus 7i, well, all you need to do is just add 2 plus 5 to get 7, and 3 plus 7 to get 10i. So the sum of these two complex numbers is 7 plus 10i. We'll see another example here in a minute. Now, to take the difference, meaning you take the one minus the other, all you need to do is subtract the real parts and subtract the imaginary parts. So if you have 2 plus 3i minus 5 plus 7i, well, you're going to take 2 minus 5 to be -3. That's the real part of the sum, of the difference. And then you have 3 minus 7, which is -4i. So -3 minus 4i will be the difference of these two complex numbers. So some more examples here. Suppose that we have 3 minus 2i plus 5 minus 4i, and we're just going to simply add the real parts together, 3 plus 5, to get the real part of the sum, and then take -2 plus -4 to get the imaginary part. So that gives us 3 plus 5 is 8, -2 plus -4 is -6. So 8 minus 6i is going to be that difference, of that sum of these two complex numbers. Now we're going to take the difference between those two numbers. We'll just take 3 minus 5 to get the real part, and -2 minus -4 to get the imaginary part. simplify, and you get negative 2 plus 2i. Where did the 2 come from? Well, negative 2 minus a negative 4. You know that the negatives cancel, so that's negative 2 plus 4 to give 2. Now, we have seen how to add and subtract complex numbers. Now we will multiply. And if you remember how to FOIL out the product of two binomials, then this is exactly the same thing. We'll FOIL this out as well. We'll, in this example here, we'll take 3 times 5 plus 3 times negative 4i plus negative 2i times 5. And then finally, we'll have plus negative 2i times negative 4i. Now, 3 times 5 is 15, right? And 3 times negative 4i is going to be negative 12i. And negative 2i times 5 is negative 10i. And negative 2i times negative 4i is going to be, well, negative 2 times negative 4 is positive 8. Then you have I times I is I squared. But remember that I squared is negative 1. So we're going to have a minus 8 there. And 15 minus 8 is 7. So we're going to have a 7 minus 2i. Sorry, 7 minus 22i. 7 minus 2i is the product of these two complex numbers. You multiply two complex numbers and you get a complex number. So that's the product of two complex numbers. Just FOIL them out. Here's kind of the formula here. So match this up with our example up here. So this right here, the AC minus BD will be the real part, and the AD plus BC will be the imaginary part. Conjugate. When you take the conjugate of a complex number, all you're doing is, if you have A plus BI, then the conjugate is going to be A minus BI. And the conjugate of A minus BI is going to be A plus BI. The notation is where you have an overbar on top of the complex numbers. By the way, we typically use the letter Z to stand for your generic complex number. So for example, if you have Z is equal to 3 minus 2i, then the conjugate Z bar is going to be 3 plus 2i. So if this is a minus, then the conjugate's going to be a plus. And it turns out that if you take any complex number, times its conjugate, what are you going to get? The middle parts are going to cancel each other out, like you see here, and you're just going to be left with 9 minus 4i squared, but I squared is negative 1, so this will be a minus 4 times a negative 1, which is plus 4, so 9 plus 4 is 13. So a complex number times its conjugate is always going to actually be a real number. Okay? So this is what this little theorem tells you, that complex number times its own conjugate is going to be a real number. If it's A plus BI times A minus BI, then you're going to be left with A squared plus B squared as Z times Z bar. Now, if you have a fraction with a complex number in the denominator, we need to simplify it so where this complex number is going to be written in this form. Now, this discussion is similar to rationalizing denominators. What you need to do is multiply the numerator and denominator of this fraction by an appropriate complex number that will turn the denominator into a real number. And as you can guess, we're going to multiply the top and bottom by the conjugate of 3 minus 2i in this example. So we'll take this fraction times 3 plus 2i over 3 plus 2i, which is 1, so you're not changing the value of this complex number. You're just going to change the way it's written. Now, 3 minus 2i times 3 plus 2i is 9 plus 4, per our discussion in the previous slide. And in the numerator, you have 3 plus 2i. Now, the denominator, 9 plus 4, is 13. So you'll have 3 over 13 plus 2 over 13i. And that's how we will write our answer whenever we have a fraction or a ratio of complex numbers. Like this one right here, 3 minus 2i over 5 minus 4i. You'll do something similar. Multiply top and bottom, meaning the numerator and denominator, by the conjugate of the denominator, 5 plus 4i. Like you see there. Now multiply out the numerators, 3 minus 2i times 5 plus 4i. FOIL it out like you see here. In the denominator, you'll have 5 squared plus 4 squared, which is 41. In the numerator, you'll have 5 plus 8 is 23. 12 minus 2i over 41, and you'll split that up to be 23 over 41 plus 2 over 41i. Again, writing your answer in the form a plus bi. That's what they mean by standard form. Now, suppose that we've got z is equal to 3 minus I, and w, another popular letter to stand for a complex number. Suppose w is equal to 2 minus 5i. Well, what is z over w? Z divided by w, that means 3 minus I divided by 2 minus 5i. So, and then conjugate that denominator like you saw in the previous example. Multiply that out, simplify, and there you go. If you see z plus w conjugate, well then all you need to do is just add z to w, and then take the conjugate of that result. Now, z plus w is 5 minus 6i, right? Because 3 plus 2 is 5, and negative 1 minus 5 is negative 6. So, and then the conjugate of that is going to be 5 plus 6i. So when you see this right here, this means take the conjugate of z plus w. The order of operations is that you add the two complex numbers first, and then you take the conjugate. Now in here for part C, we're going to take z plus its conjugate. Now when you take a complex number plus its conjugate, you're going to actually have the imaginary parts cancel each other out, and you'll have twice the real parts. Okay? Conjugate of a real number is the real number itself. After all, if you have a real number like 2, for example, you could write that as 2 plus 0i. And then the conjugate of that will be equal to 2 minus 0i, which is equal to 2. And then the conjugate of a complex number is the number itself. How come? Well, I'll just do a quick little proof. A plus bi conjugate. Now the conjugate of a plus bi is a minus bi, and then the conjugate of a minus bi is equal to a plus bi. And then the conjugate of the conjugate of the conjugate of z is equal to z conjugate. So pairs of conjugates cancel each other out. By the way, taking the conjugate of the sum of two complex numbers is equal to the sum of the conjugates. Why? Well, suppose we have z is equal to a plus bi, and w is equal to c plus di. Well, z plus w conjugate is equal to a plus c plus b plus d I, and we have the conjugate there, and then that'll give us a plus c minus b plus d I for the conjugate, but then this is a minus b I plus c minus d I. But then that's z conjugate plus w conjugate. Okay? Oh, let me clear the ink off the screen so we can see what's going on here. And the same holds true if you're going to take the product of two complex numbers and then take the conjugate of that product. Well, then that would be the same as if you were to take the conjugate of each of those numbers and then multiply. So in other words, if you have the operation of multiplication and conjugacy, it doesn't matter what order that you conjugate and multiply. You can do the multiplication first and then conjugate, or you can conjugate first and then multiply. You get the same result. Now let's talk about taking powers of real numbers. Now, of imaginary numbers. Now, we know that I squared is equal to -1. Now, I cubed is equal to I squared times I, but I squared is equal to -1, so you have -1 times I. Now, I to the fourth power is equal to I squared times I squared, but I squared is -1. So you have -1 times -1, which is 1. So I to the fourth power is equal to 1. That's important to know that. I raised to the fourth power is equal to 1. Now let's move on to the fifth power. Fifth power of I, well, you could write I to the fifth power as I to the fourth times I. But I to the fourth power is 1. So you have 1 times I, which is I. So I to the fifth power is 1. I to the sixth power is I to the fourth times I squared. But I to the fourth power is 1. I squared is -1. So you get -1 is what I to the sixth power is. I to the seventh power is I to the fourth times I cubed. I to the fourth is 1. I cubed is -1. Per our discussion over here, I cubed is equal to I should say. So I to the fourth times I cubed is going to be 1 times -I, giving you -I. And then I to the eighth is going to be I to the fourth times I to the fourth. Or in other words, I to the fourth squared. But I to the fourth is 1, like we saw over here. So that's 1 squared, which is 1. So in other words, when you have I raised to a high power, you can actually split off some power of 4 or some multiple of 4. So for example, if you have I to the 33rd power, if you look at the number 33, what is the integer less than or equal to 33? Closest to 33. That's a multiple of 4. And the answer is 32. So you could write I to the 33rd power as I to the 32nd power times I, as in I to the 1 power. Remember, the powers can't, they add. Anyway, I to the 32nd power means I to the 4th power raised to the 8th power. Remember the product rule for those powers, for those exponents. But I to the 4th power is 1. So this is 1 raised to the 8th power, which is 1, times I, which is just I. Okay? So I to the 33rd power is equal to 1. Let's do another example. I to the 82nd power. Again, think about what integer less than or equal to 82, closest to 82, is going to be a power of 4. And I would say 80, because 80 is equal to 4 times 20. So you could write I to the 82nd power as I to the 80 times I squared. Again, those exponents add. But I to the 80th power is going to be I to the 4th raised to the 20th power. But I to the 4th is 1. 1 to the 20th power is 1. I squared is -1, by the way. So I to the 8th power, sorry, I to the 82nd power is equal to negative 1. So you see a sort of cyclical pattern for powers of I. You start off with I, multiply by I, you get negative 1. Multiply by I again, you get negative I. Multiply by I again, and you get 1. And it repeats, and as you go in this clockwise direction, round and round the horn. Now we could talk about writing powers of complex numbers. If you remember how to do powers of binomials, then by all means, then go ahead and use those same special products. Like, for example, we know that x plus a cubed is written like that. X cubed plus 3ax squared plus 3a squared x plus a cubed. But in this case, x is equal to 3 and a is equal to negative 2i. So x is equal to 3, a is equal to negative 2i. So that's what you will replace x. You'll replace x by 3 in this little formula here and replace a by negative 2i. And then simplify. And simplify. And simplify. And it works out to be negative 9 minus 46i. A complex number raised to a power gives you some other complex number. Now, going back to solving quadratic equations. Remember from the previous section that if the discriminant b squared minus 4ac, if that was negative, then we didn't have any real solutions. But now that we have opened up the possibility of having complex solutions, now we could talk about having solutions for all quadratic formula or quadratic equations. Remember that the square root of negative 1 is I. So if you have the square root of the negative of a number, then that's the same thing as the square root of that number times I. And we call that the principal square root of whatever negative n is. So for example, square root of negative 1 is going to be I. Square root of negative 9 is going to be 3i. Square root of negative 18 is going to be 3 times the square root of 2 times I. That negative 1 multiplier can come right out. Square root of negative 1 is I. So this will be square root of 18 times I. And of course, we know that, excuse me, that 18 is 9 times 3. 9 times 2. Square root of 9 is 3. So that's why you have 3 root 2i. So if you have the equation x squared equals 9, you could write that as x being equal to plus or minus square root of 9, which means plus or minus 3. But if you have x squared plus 25 equals 0, that means that x squared is equal to negative 25. That means that x is equal to plus or minus the square root of negative 25, which is, square root of 5. Square root of 25 times I, but square root of 25 is 5. So x is equal to plus or minus 5i. Which should make sense. 5i squared is equal to negative 25, and positive or negative 5i squared is equal to negative 25. So whether it's plus 5i or negative 5i, you square that and you get negative 25 plus 25 is equal to 0. Now, for the general equation ax squared plus bx plus c equal to 0, we will potentially use the quadratic formula. And if b squared minus 4ac is negative, then we could potentially have complex solutions. Let's kind of warm up by looking at this equation here. X squared minus 6x plus 13 equals 0. We have a is equal to 1, b is equal to negative 6, c is equal to 13. Okay? So that means that the discriminant, b squared minus 4ac, will be equal to 36 minus 40, or minus 52. That's equal to negative 16. We have a negative discriminant. That means we're going to have complex solutions. And here's what the quadratic formula tells us. Here's your negative b plus or minus the square root of the discriminant over 2a. So, simplified, there we go. Now, square root of negative 16, the square root of 16i, square root of 16 is 4. So we have 6 plus or minus 4i over 2. And then you could divide the 6 and the 4 by 2. So you have 3 plus or minus 2i. 3 plus 2i and 3 minus 2i. Notice that you had a conjugate pair. And that's important to understand, that if you have complex solutions, that those solutions will be conjugates of each other. They'll be a conjugate pair. So let's do some other examples here. Let's talk about, looking at the quadratic equation and determine what sort of solutions that we're going to have. For this one right here, we have a is equal to 2, b is equal to 3, and c is equal to 1. So let's look at the discriminant. B squared minus 4ac. And that works out to be 1, which is positive. Positive. That means that you're going to have what? You're going to have real solution, 2 distinct real solutions, in fact. Let's take a look at this next one. You have 5x squared minus 2x plus 4. A is equal to 5, b is equal to negative 2, c is equal to 4. And go ahead and calculate the discriminant. The discriminant works out to be a negative number. That means that you're going to have a conjugate pair of complex solutions, because you have a negative discriminant. And for this next one here, you have a discriminant that is going to be 0. Which means that you'll have one real solution. And we say that the quadratic function has a double root. Okay, so that is it for today. And I will have homework posted. And by the way, all the PowerPoints are loaded up on Blackboard as well. And we will see you tomorrow.